Hey, Barbara.
Hi, Caitlin. Can you
How
hear
are
me?
you?
Hi, do you hear me?
Yeah, I can hear you.
So I
Uh,
started sharing the screen. I don't know if you wanted to share screen before me.
um, actually, yes, there's one. I just want to, but make sure everything works.
Okay, so then let me just stop sharing.
Okay. So did you, did you check and test any of your slides, or everything seemed okay?
I think it's fine. Yeah, I'm hoping. I've done this before,
Great.
but
It looked fine. And do you need any other, do you have, you had cursors and all the things you wanted?
I think everything is okay. Let's see.
Yeah, we can always switch things up. And just to let you know, one thing we have tried to do with this talk series, with some success, is keep it a little bit more interactive than uh, the typical Zoom talk.
Yeah,
And so, is that okay with you to have me
of
tell people
course.
they can?
I prefer it that way.
Okay, great.
Actually, what I find also a little bit weird is when I don't see the other, the participants. I don't see. So this is not. If
Yeah,
at least if I can hear them, if they ask questions, this is good.
yes, and I will ask people to unmute their video when they ask a question as well, just so you can at least see their
Yeah.
maybe see their faces a little bit depending on your screen configuration. And then I am going to start with I do have a quick slide to advertise we have a fellowship that I want, not a fellowship, well, we have that too, actually. I'll mention it to you while you're here. Then we do have a theoretical postdoctoral fellowship advertised right now. If you happen to have anyone who's looking for a position.
I know that there's one person that's logged in right now, Christina. I don't know if she's she's looking for jobs. She's in the last she's on the last stretch of a PhD, but probably she's already applied. I don't even remember where she all applied with all.
Well, Christina, please consider U of A if you haven't applied. It's a flexible fellowship position. It's open to all fields, and it's on the AAS job register and the Steward website. I can send you the link to the application if you'd like. I'll just note it's a bit of unfortunately, the interface that HR makes us use is a little bit annoying, so I apologize in advance for that.
No problem. Thanks. It would be super nice to send it.
Yeah. All right. Let's see. We'll hang out a few more minutes because people are sort of slow coming in, and I'm just going to start a screen share so I can show this. This is for our people, but okay. Hopefully, is that showing up for people? The 2021 Graduate Student Research Prize. Okay, good. So how's Munich? Are you surviving okay?
Yeah, it's not. Actually, I don't feel very much this lockdown because of I kind of like don't do a lot of the things that you can't do anymore. The only thing that annoys me a little bit is this lack of skiing, lack of, but you cannot go to Austria at the moment, not even for hiking or anything like that.
I see. Oh yeah, and that's where all of the Alps are, right? From Munich, the closest Alps are all in Austria, of course.
Yeah. But you can also, there's also like a very beautiful place in Munich, but they decided to keep all the all the cable cars closed in Bavaria now until the 10th of January or something like this. So it's
yeah. I guess it just means you need to hike up the whole way.
Yeah, that's right. So we all have obviously we all have like ski tour, so cross country skis.
Yeah.
Which is okay, but it's difficult with the two children.
Yes.
To drag them along. Anyway, we'll be really fit at the end of the winter.
Yes. Yeah, we're hoping to get some skiing in this winter as well, but I suspect we'll mostly be doing backcountry, but we'll be finding a babysitter, I think, during the
That's right.
She's still a little young for the backcountry touring, I think.
Yeah. You can put it in the rucksack. How old is he?
She's 21 months.
Oh wow. Okay, so
Yeah.
so like
Sort of heavy and, you know, still carryable, but a little heavy. Have you done touring with the kid in the backpack before?
I did, but when they were smaller. But our youngest one is now almost 3. He would be 3 in a couple of months, and he started skiing when he was 2. So
Okay.
this was actually quite good. I just put him on the normal skis, and then I had a thing for climbing, you know, this, and I just pulled him up with a rope.
Yeah.
And it was fine. So he just stand there on the rope, but you know, you also had a harness.
Yeah.
So you didn't have to, you know, keep hold. It's too tiring. And you just had a harness. I had a harness, and it just and you can't go up Matterhorn or anything like that. Yeah,
No,
just
no,
go up a small slope, and then you let him slide down. But it was enough.
Well, we will have to give it a try this winter. I think she'll be up for it. So
yeah, 2 harnesses and a rope is fine.
we got that, and I can get the skis. So all right, I'll give people a few more minutes to trickle in. It's people are a little slow after the holiday weekend, I know. Yeah, it's funny, the email that went out, normally there's a button that you can click, but for some reason that button didn't show up in the email this week. So you have to like type in tap. I wonder if we should send another email out. Rosie, are you there?
I am. I spoke with Angela about that this morning, and I'm hoping everyone knows to enter TAP Arizona as the meeting ID at this point. But I can respond to it, at least in Astro, if you want to. I can put that link in.
Yeah, maybe if you just want to send out a quick email, just noting that that's a way to join, is either typing in TAP Arizona or sending out the link again, just because I know I spent a couple minutes clicking around, and then I was like, oh, I'll just enter the meeting ID. I know I can do that, but
absolutely. Let me get that out right now. Just
okay, thanks so much. I really appreciate it. And while we wait, I'll just mention, as you can see on the screen share, I just wanted to remind everyone about the 2021 Grad Student Research Prize. So current graduate students or people who have graduated in the last year are eligible. And it's anything between January 2019 and December 2020, and the deadline is January. So the application is pretty simple. And there's more information on the website if you are interested or you have a student who might be interested. And then the other announcement I will just make before I introduce Barbara is that she has agreed to meet with people. And there's a link to a schedule here that I just put into the chat. Hopefully these times look okay. And if they don't, just let us know. So if anyone wants to schedule a time to meet with Barbara, there's a schedule there, or you could just contact her independently. We're still trying to navigate exactly how to make these virtual visits seem a little bit more like visits and a little bit less like, you know, TV shows. So, okay, I'm gonna stop my screen share and I'll let Barbara go ahead and take over, and then I will introduce her once her slides are up.
So I think you can see it, right?
Yep, that looks great. All right, well, just so that we don't run over time too much, I'll get started. So it's a great pleasure to introduce Barbara Ercolano, who is at the Ludwig Maximilians University of Munich and the University Observatory. Unfortunately, we incorrectly entered her affiliation as having something to do with the Max Planck Institute, and although they are everywhere in Germany, they are not in charge of her her group there. She's also one of the main leaders of the LMU's Excellence Cluster, which is funded by the DFG. Barbara has made some really phenomenal contributions to the theory of star and planet formation. One of the things she's most well known for is the development of a 3D photon ionization and radiative transfer code called Moccasin. She's an expert in especially the impact of X-rays from young stars on their protostellar disks, and has done a lot of really foundational work on how radiation can contribute to the dispersal of protoplanetary disks and impact planet formation. So with that, I will turn it over to Barbara. And I just want to remind everyone that we do like to keep this sort of interactive and informal as best we can. So you can type a question into the chat, or you can politely unmute yourself and interrupt. And I just ask that if people want to unmute their video as well when they ask a question, just so that we can get a little bit more face-to-face interaction. So if you're comfortable doing that, that's great. And if you'd like me to ask the question for you, again, just you can send it to me privately in the chat, and I will do the interrupting and ask the question. So, all right, with that, I'll let you take it away, Barbara. Thank you.
Thanks, Kate. That's right. Please do interrupt me because I have bad history of not seeing these chats at all, particularly if I'm sharing my screen. I actually don't tend to see the chat. So I'm sure there's a way to do it, but I haven't worked it out yet. So please do interrupt me, and let's keep it informal. So I have also very informally prepared for this talk. So you are very welcome to interrupt me at any time. This talk is a collection of what I've learned with the help of many other people over the last 10 years or so about how we think that disks, protoplanetary disks, disperse after a few million years. And obviously this has consequences on the disk ability of making planet. Obviously, when they finally disperse, this has particularly bad consequences for planet formation. But even the time before the final dispersal, this crucial time when the dispersal sets in, ends up having a large impact on the final planetary system that you might get out of the process. As I say, before I go on, this is work that I've done with a huge support of a very brilliant group of people. Many of them have been funded by the DFG through this research unit, for which you see this nice little logo here, but also people through the Excellence Cluster and just generally collaborators all over the place. And so just as a very short introduction, so I know that many people in Arizona work with disks, so this is probably for most people bread and butter, so I won't go into much detail about this, but just a very quick slide of introduction. Basically, planets form, we think they form by the aggregation of small dust particles, which then become large dust particles. They might sink to the midplane, and at some point through very different processes, many of them still really open to debate in the literature, they become planetesimal and finally planets. Now, the disk is called because the disk has very high densities, and so things like particle collisions can happen many times, unlike the interstellar medium, where I guess you would have a pretty hard time to make microparticles grow to the size of planetary cores. Here you have very high densities. The gas is very thick, particularly in the center of the disk, in the midplane. And so this is the perfect nursery, let's say, birthplace for protoplanetary disks. There's also lots of gas around, so once you have managed to make the core, you can also pull up a very cool atmosphere. You can become a nice terrestrial planet with a nice atmosphere like our own, or you can become a high mass planet which has lots of gases, so you can become a gas giant or an ice giant if you're far away from the star. And so the disk basically has it all. The disk is also the source of many problems for dust formation, because disks don't tend to just sit there and be still and allow all this thing to happen quietly. They have a very young active star, in the center. So like all young things, they tend to be very active, overactive compared to the older version of the stars like our sun. And so if this is a picture of the surface of our sun, you can imagine something about 10,000 times angrier than that. That's a young star, has a lot of X-ray producing processes, is magnetically active. And these X-rays, obviously picture not to scale here, X-rays have, let's say, the good habit and the bad habit at the same time to penetrate very deep distances into the disk. The reason is because they can penetrate very large columns of gas, because they don't care much about the hydrogen ionization cross-section. They're far away enough from it, so they practically don't see hydrogen, which is the most abundant element, obviously, so the one that would absorb UV radiation very efficiently. And they can penetrate longer distances until they basically can get absorbed by an inner shell electron of one of the metals like carbon, oxygen, and nitrogen. And obviously, there's much, much less of this stuff than there is of hydrogen. And so to cut a long story short, these X-rays can basically drive the chemistry, affect the chemistry all the way almost into the midplane in some places. They provide ionization, which basically charges your gas and allows it to see magnetic fields that might be around. And so it couples the gas to the magnetic field. And in the past, we thought that this was basically the key to disk accretion, coupling the gas to magnetic fields, which would create a instability called MRI, magnetorotational instability, which would drive a viscosity within the disk, which then would allow angular momentum to move outwards in the disk and so mass to move inwards. So this was the explanation of how these disks could accrete, how they could lose angular momentum or redistribute angular momentum. Now it seems that the picture might be changing, at least for some time, of the disk evolution, in which outflows might simply take out angular momentum, not redistribute it from the disk. This also has the effect, obviously, of allowing the material to fall onto the star. And even for that, you need to basically take care of what the ionization structure of the gas is. The other thing that these X-rays do is obviously through ionization, they heat up the gas. And in the soft region of the X-ray spectrum, they can heat up the gas quite efficiently also in the disk atmosphere, and can basically create a thermal wind. So they can thermally unbind the gas, which is then centrifugally launched from the star. The other bad habit that this all has is that everything happens at the same time. And so it's very difficult to kind of decouple the various processes, although we still do that because we need to do that. Otherwise, we won't be able to model this level of complexity. But in theory, you should be able to take these effects into account self-consistently with each other because they occur on basically similar timescales. Now, this is the sort of image that you always have to show for a disk kind of talk. And this is an image that basically we are now getting spoiled to see. We see many of those images. These are obviously ALMA images that show plenty of substructures, and these substructures seem to be basically everywhere in disks. And we're learning, of course, a lot about this protoplanetary disk and the possible processes that might be happening in them in shaping these objects, not only morphologically, obviously, to making them evolve and affecting planet formation. Here, there's also images in scattered light from sphere, as you can see, which also shows spirals and rings and all the rest of it. However, I should say that if you're interested in understanding the global evolution of a protoplanetary disk over its lifetime, so how the material actually evolves, then this type of observations are limited in the sense this is a snapshot in time, and you don't know exactly what process is causing this exact feature that you've seen at the moment. A lot of what we have learned about the global evolution of disks is much more boring than that. It looks more or less like that. So you just basically look for disks by looking at, this is old stuff that is not done anymore, but we used to have satellites like old Spitzer, people still remember it, in which you basically see just a infrared excess when you look at a star that has a disk. You know more or less what a photosphere looks like, and you say, oh God, I have too much mid-infrared excess. What's happening? There must be a disk. More or less, this was how we knew the disks were there. There were basically spectral energy distributions that we could not explain with a photosphere star at extra infrared excess. And if you just basically go and look at entire populations in clusters, which are simple stellar populations, so they are, you assume that all the stars are born more or less at the same time and from the same metallicity, then it's easy to get an age for the entire population. And this is what you plot here on the x-axis. And then you look for each one of those clusters, which is each one of those points is a cluster. Say how many of the disks, how many of the stars in this cluster have an infrared excess. And this is what you plot here. And what this is telling you is the fraction of young stars that still have a dust disk, because they're still emitting in the mid-infrared. And if you do this, this has been done many times before. This is just one of the, this is the first Height plot, but there are many versions of this Height plot, also with the mass accretion rate, so the way you look at gas. The answer is more or less always the same. The disks don't live forever. They live only for a few million years. And then to about 10 million years, they're basically just bare photospheres. They've gone somewhere. But this is only one side.
Can I ask you a quick question?
Yeah.
So I don't know if do you know if anyone has redone this plot with Gaia distances to update cluster memberships? I mean, there's been so many of them, and of course they really haven't changed much, but in terms of a disk fraction, one could imagine that might shift a little bit if you had a better sense of all the cluster members. But I can't.
I don't know the reference net now in my head, but I remember having a conversation with Eric Lagadek about this, and I know that that people have been looking into it, but I don't know if there's been a final like let's say a game-changing publication that showed something different. Definitely there hasn't been a change in the general understanding of what the lifetime is, but maybe somebody knows more.
Yeah, Ilaria is noting in the chat that the main issue is the age of clusters rather than the distance. Yeah, I meant cluster membership, not the I understand the error bars on age aren't changing, but in terms of the y-axis, getting a fraction if you knew how many, which of the stars were actual members. That's all I was thinking, but maybe that hasn't changed much either.
You know, I think the bigger impact has been when people have done this again by comparing also mid-infrared surveys to X-ray surveys, because then they had a better fraction because they could also see the disks without so the stars without a disk, the class 3 stars, so the Wickline-Tori stars, which generally meet just in the X-rays. No, then you could be sure how many young stars there are, and this changed a little bit for some clusters, but again, I think the global picture is remained the same. But maybe Ilaria knows better. I don't see her.
No, I actually agree with what you said, and I wanted to stress one point you made, which I think is very important. Even though now we have all this millimeter data from ALMA, I think we have to be careful to use that data to learn about disk evolution, because it seems to me that those millimeter grains are more relevant for planet formation rather than disk evolution. So I agree with your point.
Yeah, thanks. So this was basically one, this is the way that I justify showing basically 20-year-old plots in the in my talk. But as I was saying, this is just one of the things that we've learned from those boring surveys, if you want to put it that way. The other thing that we have learned is basically how fast the actual dispersal is. So we know that disks live for a few million years, but once they start dispersing, how quickly does it go? And this is something else that we can see from this basically boring photometric surveys, because if you plot basically the colors of young stars, this is k-8 and k-24. So for the non-photometry aficionados, stars basically emit K, and dust emits 8 or 24 micron. And the 8 is warmer than dust than the 24 micron. So if you just have a star without a disk, then you just emit it in the K band. So you're somewhere here in this bunch of points over here. If you have a star that is dominated, the emission is very strong from the disk, then you will emit up here. So you have this population of disks, which are very clearly strongly emitting both in the 8 and the 24 micron band. Now, if you imagined that disks just evolve viscously, slowly, basically going progressively optically thin, then you should see many, many disks in this region. So going from being infrared bright to being K-band only, no? And you don't see any of those disks going progressively optically thin. What you see is basically a few disks which seem to be in between, but seem to follow a different track. They seem to lose the 8 micron band signal before they lose the 24 micron band. And so from that, we, well, this is the royal we people inferred that this second phase, the phase of this dispersal, must actually occur very, very quickly. Because if you assume that all disks, all stars are born with a disk, and all stars end up without a disk, then somehow these stars have gone from this region of the graph to this region of the graph very quickly. So we did not catch them into action as they were losing their disks. So this dispersal phase must be very, very rapid. And if you look at statistics, they say, okay, about 10% of those disks are in this weird transition phase that actually follow this track. Then you can say, okay, the dispersal timescale must be only 10% of the global disk lifetime. And so this is roughly what I have already explained. The 8 micron band is warmer, the 24 micron band comes for a little bit further out. And so if you lose the warmer dust before you lose the hotter dust, it means that you are basically dispersing the disk from the inside out. And this is again something that we got out of those surveys, that if you are having disks following these tracks, becoming basically less bright in 8 micron and then less bright in 24 micron, it means that you're losing the 8 micron first, which is closer in, and then the 24 micron. And this is roughly what you see here. You see really no disks that are in this region. This is something that basically with a couple of overexcited master students at the time, Christine Kupfer, and then there was also Daniel Meyer. They went and scanned through the old literature and looked for basically objects that will follow in this region. But before that, they basically looked at hundreds of thousands radiative transfer models and calculated these boxes. Basically, they said that basically all the disks that are primordial, so that they're optically thick in the dust, they should be over here. The stars without the disk should be here. The stars that are viscously draining should be here. And yeah, these are flat pancakes, basically, they also very rarely see. And if you basically remove the dust from the inside out, then you follow this path. And they compared it with many, many star forming regions. These are in several papers that we did at the time. And we always find that clusters more or less evolve along this track rather than evolving around that track. And so we don't see this. Disks start in high mass, high accretion rates, and slowly spreading until we don't see them anymore, which is what would happen is if only a viscous process would be acting alone. Instead, we see disks sitting there doing nothing, being optically thick, and then about 10 million years later, being gone, being debris disks or whatever, and only up every now and then we see basically rare transition disks. So disks with then an evacuated inner hole. This is what I mean by transition disks here. although now this term has become very confusing because everything is a transition disk in some way, everything has some kind of structure, and so let's call it disks within the cavities in the dust, in the small dust.
And just to highlight that point, if can I get you to put a number on rare based on this interpretation of the meaning of transition disk? Would you say 10%?
Well, the 10% was, I think it's a safe number because it was before ALMA, which confused everything. So it was when we were looking at the mid-infrared, which is basically emitted by small dust grains, which tend to be then coupled with the gas. And so you're generally talking about those disks that have lost the signal in the mid-infrared, but also have then necessarily there can't really be much gas there either because they would be coupled with the dust. Now, of course, even in the ALMA time, we had pre-transitional disks, weird disks that had lost the mid-infrared signal, but they still had some very, very small amount of dust very close in. And so this was Catherine Espaya found many of those. This was her specialty. And see, even then was confusing, but now it's even more confusing. And I'll show you this in one of my last slides. We basically have transition disks found by ALMA in the millimeter, which are perfectly healthy SEDs. They look like normal disks. And so this is obviously something else. And this is something that you have a trap that is stopping the millimeter disks going in, but it's allowing the gas to go through, and with that also the small grains. And so I think 10%, 5% or 15%, so everything is allowed. They're of that order. Okay, so this is again just summary. 2 timescales, one long, one shorter. And so this kind of motivated the development of models that could respect this 2 timescale behavior. So a disk doing nothing for a few million years and then being, I say photoevaporated away, I shouldn't say being dispersed away very quickly. And so how does photoevaporation actually works? This is a very broad brush picture to which I think most of the community agrees. Anything beyond this picture, we don't agree on anything. But on this picture, I think we agree. Although we still we don't agree either, because now I have mass moving in and angular momentum going out. And if you have an MHD wind, you don't have angular momentum moving out. You have angular momentum going up. But so even on that, we don't agree anymore. But up to about like a year ago, we used to agree on that you have an accretion disk, mass is moving in, angular momentum is moving out. A star is irradiating it and is heating up the gas in it, and it's creating this thermal wind that I was talking about before. Now, the wind also has a wind rate, has a mass loss rate. When the mass loss rate in the wind is higher than the mass accretion rate, then the wind wins. And there will always be a time in which this happens, because the wind rate is basically constant through the 10 million years of the lifetime of the disk, because it pretty much depends on the intensity of the radiation field from the star, and that stays constant. But the mass accretion rate goes down, and this is something that we also have seen observationally as the star ages. And so at some point, the wind wins, you have a gap, and now the inner disk is completely decoupled from the outer disk, and it can drain onto the inner star. And you have just basically the outer disk left being completely fried from the star, and this then is removed from the inside out. And then I say all these different lovely people agree with each other more or less on this picture. There's been many models now which have done this. Some of them have followed the evolution of the surface density distribution, and this is more or less what you expect from this. However, as you all know, the devil is in the detail. That is the detail. The mass loss rates from these winds are very uncertain. I would say that depending on what type of models you build and what are your assumptions, what are the limitations of your physics, you get a bit of a different answer. like 2 orders of magnitude. And here it's in basically the photoevaporation profile. So this is not just the total mass loss rate, but this is telling you how much mass the disk is losing where as a function of radius. No? And as you can see, if you look at different models, you also have different profiles. And so different parts of the disk are affected differently in these different models. And you might say, who cares? You broad brush picture is all that we care about. But actually, I don't particularly care how this disperses. I care how this dispersal affects the formation of planets. And it turns out that exactly this detail over here is what matters to the formation of planets. It's very different if you're removing mass at 500 AU, like in this red line, or if you're removing a 2 AU, or if you're removing a 10 AU or an 80 AU. And how much mass, how quickly, at what time during your disk evolution, this also makes a difference. And just to give you a couple of examples of practical applications of this, one was the idea that photoevaporation can help forming planetesimals by removing the gas and increasing dust to gas ratio. This is something that tends to be important if you want to trigger, for example, the streaming instability. You need to have a high dust to gas ratio, and since photoevaporation can only really remove small grains from the wind, which are entrained in the wind, leaves basically the large grains behind, then increasing the dust to gas ratio. Well, depending on what profile you use, even using exactly the same mass loss rates, you get a different answer. So for example, if you look at this paper here by Daniel Carrera, which is the profile of UMA, Gorty, which had that tail, remember this red tail at very large radii. Well, it turns out this very large tail, very large radii is instrumental to creating like 10 Earth masses of planetesimals at 1,000 AU in a disk very quickly, very soon in the evolution of the disk, about 2 million years. Then you would say, yes, this process is definitely important for photoevaporation to the creation of planetesimals. It can have a very big impact. Now we did the same thing actually at the same time using our own profile, which removes mass much closer in, between 10 and 50 AU mainly. And we get to the opposite answer. If you look, I should point out that the axes have also changed here. So we remove, we can make, really if we tweak everything to be the best, maximum like about 1 Earth mass of planetesimals pretty late and very close into the star. So our answer is that no, this is not really the major channel to making planetesimal for planet formation. I would even have trouble making enough stuff for a debris disk, I would say. So and that really all that changed in these two models, same disk, same assumptions, just switching these two lines. And so you see that it's not really a detail. It's really something that is very important to work out what the actual profile of your mass loss is. The other thing, if you now fast forward in the life of a planet, the planet has formed and is now a young Jupiter that is moving through a disk, being pushed around by the gas, so migrates. There was always the thought that photoevaporation, by simply removing the gas in the disk at specific location, could affect the final distribution of giant planets once the disk has gone, basically providing a stopping location. And there were many, the first models were by Richard and Ilaria. We repeated this, just simply again, switching just between two photoevaporation models, two different profiles, and we noticed that we started getting completely different distribution of planet, which is obvious if you think about it, obviously, because if you make in the hole at different times and in different places in the disk, then you're affecting the parking location. And this is another work that showed the same thing, also taking into account of UMA's profile. Again, different answers. So as a final reason, again, photoevaporation, why we do photoevaporation models is because finally photoevaporation is a key ingredient in planet population synthesis code. Every single planet, a population synthesis code, has some kind of photoevaporation in there. Otherwise, they don't make planets, they just make brown dwarfs. They have to remove the gas at some point, no? Otherwise, planets keep growing. And it turns out that it also affects finally the final synthesis of planets that you get. So this was now a paper by Carlo Manara and Christophe Mordassini and collaborators, in which basically they compared now not the planet population synthesis, so not the planet statistics out of a population synthesis, but the disk statistics out of this population synthesis model from the planet code that they use in Bern. And what they found, basically several populations of disks in this evolution, in which you see this is this population C is the population of planets, of disks with planets. This population B is the population of disks that are photoevaporating away. And if you compare it with the observations, you see that these models have problems with this population of photoevaporating disks, which are far too low mass. In fact, the observations show more or less that the disks should become photooperated much younger over here. And again, this is just a simple switch of photoevaporation model could fix this. They use here a very low wind rate, so in very old models by Cathy Clark for EUV. And if they switched to a more current model of X-ray or also FUV by UMA, you would see that with much higher mass loss rates, which are roughly 10 to minus 8 solar masses per year, you will fix this very quickly. And so, cut a long story short, we need to get this right. If we want to do quantitative planet formation models, we need to take into account of how the material is evolving within the disk. And so the best way to do this would be to just have sure observational signatures of these processes, which we could be easily inverted to get mass loss rate or conditions in the wind, for example, densities, temperatures, which you could then compare to the models and not say who's right, who's wrong. I am perfectly convinced that we're all wrong, but to just basically try and converge to something that is more realistic or closer to observation. And I should say that Ilaria has done really pioneering work in this, in pushing these observational disk winds. And this is from one of her recent reviews, in which basically we are showing here what are the possible diagnostics of winds. So if you think of an emission line that is emitted in the wind, and you think the wind is blowing towards you, clearly the wind is blowing the emission line towards you. And so it's causing this line to be blue shifted when you observe it. That's the best indication of a wind. We know that this was the best indication of a jet. So if you see a line formed in a jet, you also see it very much blue shifted. But of course, there you see it like blue shifted by hundreds of thousands of kilometers per second, depending on the type of jet. And in the case of disk winds, you're expecting much smaller blue shifts, so only a few kilometers per second. And so this is a very challenging observation to make. And as I say, Ilaria's group has really been the people who have collected an enormous amount of observations, both in oxygen 1 and in neon 2, to show the presence of disk winds. Now, the nature of these disk winds is still to be debated, and this is what I will show you in a few slides. So the first thing that Ilaria noticed was the neon 2 line. This neon 2 line, which had a few kilometers per second blue shifts. And so we all went and modeled this, and Richard did a very good job at doing this with the EUV model, which has 10 to the minus 10 solar masses per year. And we also, with James, managed to fit this line, I would say, just as well. And we have a mass loss rate about 100 times higher than what Richard says. So basically, this is very difficult. It's just to show you that this line on its own is probably not not very useful to invert to get mass loss rates, although Ilaria did find a workaround by combining this line with radio observations, but I don't have time now to go into that. Another interesting line, and here I'm showing this blurred image for historic purposes, because this was basically the first observation of this slight blue shift in the oxygen 16300 line. This is a Hartigan paper. There was quite a large survey, so a few tens of classical tourist stars. And you basically see clearly that you have a high velocity component, so a jet or some kind of very strong outflow. There's a few hundred kilometers per second, but you also have a low velocity component. And this low velocity component is only a few kilometers per second blue shifted. And this already helps you understand that actually this wind must be somehow quite rich in neutral oxygen to emit the line so strong in the wind. So this kind of already rules out a wind that is fully ionized, like an EUV wind. But there could be other types of wind, also an FUV wind, and the line could be emitted differently. Or it could be a completely different type of wind, which I will be talking about later. But again, I'll go ahead chronologically. We were very happy once the new observations came out from Ilaria of this line, which I will show you from Ilaria's group, that we could match it really nicely. So we thought, oh yes, we can understand everything about this line. And we even titled our paper Oxygen 16300, the smoking gun for X-ray photoevaporation. So we were really convinced. And of course, they had to go and get more spectral resolution. And they found out that this line is not one line, this line is actually two lines. And so the glory and joy for this paper lasted, I think, a few weeks until the Simon paper came out and showed us that, hang on, here this huge component that we have absolutely no idea where it's coming from our models. And so there's many other papers. As I say, this group has been very successful in obtaining and producing these beautiful data sets. And the broad components seem to be basically present, particularly in primordial disks, so disks without the cavity. And so Ilaria came up with this explanation in which you might have an MHD disk wind, which is very close to the central star, and it has to be necessarily a wind that is driven by magnetic fields because it's well inside the gravitational radius for a photooperative wind. So it cannot be a thermally driven wind for the temperatures that we know must occur in the disk. And this seems to be corroborated by the fact that many transition disks, so disks with inner cavities, do not have this broad component. Now is the question, what is the narrow component coming from? You have this disk wind that is coming from further out. Is this now the photooperative wind? Or is this also some kind of magnetic disk wind that happens to be disconnected from the inner part? And so this is where basically we are at the moment with these observations. We have been trying to model them, also trying to assume an MHD wind model. I note here that we could use, of course, many of the MHD calculations that exist to do this, but it will not be useful because the current MHD calculations for MHD disk winds, non-ideal MHD calculations, they don't go close enough to the star to actually catch the emission region for the oxygen 1 line. So it's very difficult to do this with the current state of calculations, but there are efforts also within our network to produce more advanced MHD calculation. Oliver Gressel is leading this effort to try and get closer in and particularly get rid of this base density, if you know this kind of observations that they have to have in this observation, because at the moment all the oxygen 1 is coming from regions that should be empty and they have the base density of the simulation. So for that we decided to use an analytical model, thanks to Lee Hartman that helped us with this. And by using this very simple model, we can basically reproduce a lot of the a lot of the features that we see, particularly in the broad components of these lines. This is was work done by Michael Weber, as he was a master's student. He's now PhD student in my group, but he's working on different things. And he also joined the MHD wind with the photoevaporation wind and could obtain these complex profiles with basically narrow and broad components together. There's lots of questions that are still open on this, and we're still very far away from being able to use the model to detangle the different components. And so we hope that in the future we'll be able to also have more of models that can look at these other types of observation, molecular lines, CO lines, for example. And we have also investigated now the thought of basically looking at this, looking for these winds using the dust. So this is work that Raphael Franz has been doing. Again, in my group, is a PhD student. He calculated the entrainment of dust grains from these photooperative winds and created an RADMC observations, RADMC models. Here is a 1.6 micron, this is one of them, and compared basically a case without a wind with a case with the wind, in which you do see a more extended emission. But this is basically a best case scenario in which the base of the wind is very well populated by small dust grains. If you try and do this self-consistently with a disk evolution model using Bernstein dust evolution code in a disk, then you have a much more pessimistic view into basically you see absolutely no difference between the wind and no wind. So these winds are very tenuous at all. And so if we're now trying to see what the effect would be in polarization maps, and this is work in process that hopefully Raphael will be able to publish very soon.
Barbara, can you just tell us what the physical scales are on those images?
Yeah, I cut them out with purpose because they were so small and you couldn't read them anyway. So more or less here, I would say it's about 100 AU of the order, so 100 to 100 AU. So the inner part, I would say 20, 30 to 40 AU is the stuff that is redder.
Okay.
Yeah, so they were so small that I then got too lazy to put the.
Well, I mean, the details are. I just wanted to make sure it was hundreds, not thousands of AU there, or just.
No. This is just a standard disk. Yeah. Okay.
Sorry, Barbara, to interrupt you. I also wanted to ask you something about this slide, but which will be where is the base of the wind, basically, in terms of the scale height of the gas?
Well, you see very badly in this image because this is a RADMC 3D image. So this is it's like a map, so it's been collapsed for the viewing angle that you're looking at, 60 degree or 75 degree. So there are better images that I don't have here, but the scale of the base of the wind is basically depending very much on the scale height of your disk, but the base of the wind is at a column of 10 to the 22 from the top, let's say from the central star, because this is the penetration depth of the X-ray. So depending now on your underlying this model, this translates into a scale height. So
I see. But this result I'm just curious because I'm wondering if the difference between the two results depends on where is the dust settled basically.
Yeah, that's right. That's exactly that. That's exactly that. That's what I meant. So if this here we just basically assumed everywhere ISM distribution of dust with an MRN size distribution on the left hand side, and on the right hand side we instead coupled, so bootstrapped a model that has dust growth settling and from Till Bernstein's calculations to our models, and then all of a sudden we had much less grains at the base of the wind. So obviously if they're not there, they can also not be entrained. And so that's exactly what's happened here.
Yes. Thank you.
No problem. And so yes, you can go and play different games of indirect tests of photoevaporation, which we have done over the years, and I won't bore you with all of them, because of course, we are convinced that we are right. So we always found that we could match these things, but of course, other models should do the same to see whether they match certain other indirect tips, let's say, that nature might be giving us. One of them is here. This is now an old work about the m.m squared, Maximilian m squared relation that basically magically reflects the X-ray luminosity function. And of course, this sounds like one of those basically Masonic numbers that fit everywhere. Of course, it could be completely a matter of chance. But if you look in this paper, there is also a perfectly rational for me explanation of why this should be the case if X-rays are driving the evolution of the disk, where again, it's circumstantial evidence, and all these other papers have just as good explanations for the occurrence of this relation, if not better. You can also go and basically really use your models blindly. So you say, okay, now I won't tweak anything in my model. I just take an object for which I know really a lot. So I know the X-ray luminosity, I know the mass accretion rates, more or less the age, I know the presence of different rings, and then try and see whether I just plug in my model constrained by all these other initial conditions, whether I can get what is observed. And we did this for TW Hydra, and we were very happy that we could explain basically the small inner cavity that you see at 1AU. So this was the image by Sean Andrews in 2016. The other thing is, again, you can, we care about these models because we care about what the effect is on the planets. And the one thing that we also did is, if it's true that X-ray photoevaporation is affecting the final distribution of giant planets, maybe if the interaction between planets after the disk is gone are not as often and not as dominant, maybe we still see an imprint of this initial effect of photoevaporation on the migration rates and the parking radius. And this is basically work that has been done by Christina Monch, who's a finishing PhD in my group. So I very highly recommend it for any kind of postdoc position and fellowship position that might ever be. I heard that there might be one even in this at Arizona. Christina is your person. And here she basically looked at what would be the imprint. How would you see it if you were to plot the semi-major axis of the present day distribution of giant planet to the X-ray luminosity of the host? This is something that you think if there was a big effect, then you might still be able to see. And what you see here is a very old population synthesis from the beginning of Christina's work. There's about 100 beta versions of this, but since we have not converted on the final version, I'll show you the original one. And basically what you see here is that we believe that planets will end up on both sides of the gap, but they will be opened by photoevaporation in the disk, no? And this gap, now the size of the gap, the location of this gap, we're still trying to work out how this depends on our very simplified approach to population synthesis here. But we do think that there should be an underdensity anyway in this plane. And Christina, at the beginning of a PhD, in fact, already in a master project, went out and looked at this in the observations. And noticed there are lots of different gaps. All the other ones can be explained by biases in the observations. Only this one cannot. And this is quite well populated all around this gap. Of course, you see much better now that I've drawn it. And indeed, the significance of this gap is not sufficient to say that there is a gap for sure. It's only significant if you could, if you would already know where the gap should be and what the size of it should be. So I'm talking about statistically significant. Otherwise, it's not statistically significant. So if you run a test in which you say the gap could be anywhere and of any size, then the presence of this gap is not statistically significant. But Christina has worked out then with an increase of the sample, which is happening now also with all the test planets, and this is an older paper from 2019, we should be able to increase the significance. And on top of that, she's now running all the population synthesis to try and understand where the gap should be and how large it would be to, again, try to increase the significance of this result. And of course, you saw before a huge gap, but this was not the scale. So this is the scale of the previous plot. So roughly it's the same size, but obviously the people of you, the ones of you that are still awake at this time would have seen that actually the X-ray luminosity is much higher in our gap that it is in the observations, but that's expected. That's because we are looking at the X-ray luminosity for present day systems, and the gap calculated here is for planets in disks. So this is a primordial X-ray luminosity. And we know that over the 500 million years or giga year for which this sample was selected, the X-ray luminosity goes down, in fact, by a few orders of magnitude. And this is now work that Christina hopes to continue now to try and understand exactly how do we track the primordial X-ray luminosity to the present day X-ray luminosity. So this is again a test that you could do that would tell you that disks are indeed dispersing by X-ray photoevaporation. The other thing is this famigerated transition disks. As I said, these are more trouble than it's worth because you just don't know what they are. But we do try every now and then still to try and understand transition disks. We even have a whole research unit set up for it, and in the hope that they might tell us something about this dispersal. And indeed, if you look at transition disk populations, these guys are quite funny. So you have a few which are down here with small cavities and low accretion, and some up here which have large cavities, large accretion rates. And it was worked on by James Owen and Kathy Clark, who showed that basically the two populations here are two distinct populations statistically. And so they could be two different types of objects. And in the past, over the years, we have tried our best with population synthesis models to try and see how many of these transition disks can really be explained by photoevaporation, and then look at those that cannot be explained by photoevaporation to see whether they are weird in some way. So maybe that if they're made by planets, if we can see the planets, if we can see signatures of planets for those very large gap disks. And we have made many of those different population syntheses, as you can see, with different assumptions, different metallicities. And indeed, a large fraction of them can be explained by a simple disk dispersal model. But it's very clear that planets also form and that they do affect the disk. And indeed, if you look at many of the disks that we cannot match with our models, they are basically disks which, as Caitlin asked me before, I answered that question already. I said I'll talk about it later. There are disks that they wouldn't have been picked up as transition disks by Spitzer, but there are disks that have been picked up by ALMA, continuous observations of transition disks, which have shown these large cavities in the millimeter. But there is evidence for many of them that actually the SED of the disk looks very normal. So what you see here, if you're not used to looking at SEDs, the blue line is a model for a transition disk. So a model that matches basically the millimeter emission and assumes basically that you have a cavity also in the other grain sizes. And if it's very clear that it doesn't fit the mid-infrared region. So the mid-infrared region is just a normal disk. So it's very clear that you have small particles in the cavity. And so this disk definitely would not have been picked up as a transition disk by ALMA, by Spitzer. And so what I'm trying to say with that is that it's clear that a lot of those objects that we cannot fit are indeed objects in which you have a dust trap that has kept out the millimeter size grains. So it's made this cavity in the millimeter size and has let the gas, because they have also high accretion rates, and the small grains through. And the best thing to do that, of course, is a planet. It's a shame that we cannot see these planets in the disk. So many will say, okay, so if these are all planets, where are those planets? Well, turns out that it's really difficult to observe those embedded planets because they are covered by a very thick layer of material that is still trying to end up onto the planet. So those accretion streams, you see this in this 3D simulation that was done by Enrique Sanchez together with Giovanni Picogna last year, again in my group. And they calculated the emission, the accretion streams onto the planet and found them to basically completely obscure the planet. And this is also a similar result was found by Judith Sölagi, who looked at H-alpha emission from those planets. Again, there have been huge H-alpha surveys to find planets in transition disks, and they have returned basically no results, so 1, 2. And the reason for that is, again, if you do 3D simulations, you see that the emission regions for the H-alpha is so deep, it's basically on the circumplanetary disk, that then has to come out through a lot of material, and these are basically absorbed out. And this is a paper that from Judith. So conclusions, very simple. This dispersal, I hope I convinced you, is really central to planet formation evolution models to understand it, particularly for population synthesis purposes. Now, unfortunately, we're not yet in the position to have a model that is quantitatively predictive, and we won't be into that position until we really manage to compare with observations, and also until we understand the role of MHD winds, when do they happen, when do they dominate, and how are they different from photooperative winds. So this is the state. So take this talk as a status report of where we are. And if you enjoyed it and if you liked the topic and you want to learn more about this, you can also look at the website from this research unit. As I said, this is work that has only been possible thanks to these large collaborations with all these really nice people who are mentioned here, and many others which have been mentioned for the papers in my talk. And here's the website, and you can have a look at what we have been doing. We also have, we had some online events. We are now keeping low until the end of the first period, and we'll start again until basically in the spring with new online events on this. So thank you very much.
All right.
If there's any more questions, I'll take it.
I'll at least do clapping for some people. Thank you very much. That was a really wonderful talk. I know it's getting close to time here, but if people want to stay, I will go through the participant list and call on people to ask questions. And I'll just note, I already reposted the link to the schedule for a meeting with Barbara, so you can find that in the chat if you want to sign up. I see Andrew's hand is up. Go ahead.
Yeah. So before the questions, maybe it's the spreadsheet is not clear on what times should be chosen. I guess there should be just some awareness that it's a reasonable time in UTC for Barbara.
That's right. So a reasonable time for Barbara could be a weird thing, because anything actually after 9 p.m. for me is easier. Between 9 p.m. and 11 p.m. because at 8:30 I get rid of all the children. It's between, let's say, 4 and 7. So this time is the worst time ever. So I don't know if you heard the screaming in the back. I hope you didn't, because I have 3 doors closed in between, but this is a bad time. But after 9 p.m., which would be, I guess, in your case, 10 plus 3, so 1 p.m. So between 1 p.m. and 2 p.m. or 3 p.m. would be great.
Okay, so then we made the time slots based on, I think, what you responded a few months ago. But if you want to go in and just delete the time
Okay.
slots that you don't like and then put them in, I think I'm the only one on there right now. You can delete me, put time slots that are convenient for you, and then we'll sign up in those slots. We just populated it with ones that seemed reasonable, but we
Okay.
we certainly
I will go through it.
dinner time meetings with a small child. So
Yeah.
Yes, yes. All right, so if I can then also squeeze in a little bit of science there. So thanks for the great talk. I especially appreciate the keynote artistry with the disks spreading and becoming optically thin. It's great. So, I mean, as you know, I think I first floated in terms of triggering planetesimal formation, I first floated the idea that photoevaporation might do that, some 18 years ago. So it's great to see how the models doing that have really developed. When I sign up for the meeting, I'll share with you some recent work by Ershin Lee showing that some of those thresholds are actually a bit more generous just when you do better simulations. And then there's obviously, lots of other things. But the question I wanted to ask was on the line plot that you showed many times, comparing the 3 different flavors of the photoevaporation models. So I think I get, and correct me if I get this wrong, that EUV is obviously higher energy. So in those models, it was it can unbind the more tightly bound material closer in.
So sorry, you're talking about EUVs now?
So you had the plot you showed 3 times. It was sort of EUV, FUV, and then EUV plus X-ray for the different profiles of, I guess, where the mass.
So the classical Alexander plot
Was lost from. Yeah.
Yeah.
And so I guess I'm saying the green versus the red maybe makes sense for me because you're having higher energy photons that can unbind closer in material. But then I'm struggling to understand why adding the X-rays, which is even higher energy photons, is then
Yeah, that's to do with the fact that basically the EUV, they are all, when we talk about EUV, and in fact these models assume EUV is 13.6 eV. These are models that are isothermal, so at 10,000 Kelvin. So they assume that you have EUV radiation at 13.6 that gives you a H2 region, more or less. No, ionizes hydrogen. Now, if you ionize hydrogen, then you basically only can go as far as the hydrogen ionization front is, and then you run out of EUV photons. Instead, the X-rays, as I said, they can penetrate longer distances because they care very little about hydrogen. Because you have a guy which has 150 eV or 300 eV, and the hydrogen ionization cross-section is at 13.6 eV. The cross-section goes down as the frequency or the energy cubed. So by the time you are at 300 or 500 eV, you basically don't see that cross-section anymore. It's so small that you have a very small chance of being absorbed by hydrogen. And so you can penetrate a much larger column of gas. And so you can provide heating much further out into the disk.
Okay. Yeah,
so that's the main reason. And the FUV, they can also penetrate large columns because they also do not see hydrogen because they are not energetic enough to ionize hydrogen. They get absorbed by dust and by a little bit by carbon, but very small, depending on the energy. And so there it depends very much as well on what you assume for your dust model, how you can penetrate with the FUV.
Great, yeah, thanks.
Any other questions? I think I have some detailed follow-up questions on this, but maybe best saved for a one-on-one meeting. All right, if there are no more questions, let's thank Barbara again for talking at the most inconvenient time.
That's okay.
We understand how hard it is, and we really appreciate you making the time to be here for us. So let's You can unmute if you like to give a round of applause. And again, I'm editing the schedule now, but I hope people will consider signing up if they want to chat further with Barbara about her really interesting work. So thank you very much.
Thank you. Thanks.
Thank you. Bye.
Ciao.
Ciao.
All right, Barbara. So if she's gone. Okay, never mind.
I think Barbara left.
Yes, she did. I was going to tell her I just switched the times, but
Yeah.
she will see it, I'm sure. So,
Yes.
all right. Take care, everyone.
She was not kidding that it was a tough time. She left as soon as she was able.